So I put a announcement on D2L that sometime over the next week, you should go through the simulator tutorial that's posted on D2L. Won't take you that long. It's a simple description of a behavioral description of a circuit. I provide you the test bench, and you can go through step by step, and it generates the timing diagram. You should also make sure you understand how you can get a hard copy of that timing diagram. Of course, I guess if you have an iPhone, you could take a picture of it and attach a GIF or PNG or something like that to your assignment. But in an upcoming homework assignment, I'm going to ask you to simulate a design. I'll probably, haven't decided yet as to whether or not I'll give you a test bench, but you have to do the design and then simulate it. But that's going to be probably next week's homework assignment, so sometime by the middle of next week, you should go through that simulator tutorial. It won't take you that long.
Also next week is first midterm, I think.
I don't know, what does it say on the syllabus?
Yes, Wednesday, next Wednesday. I mean, Thursday.
It won't be on Wednesday.
Thursday, yeah, Thursday.
Okay, we talked about two types of assignments. Blocking and non-blocking. In a blocking assignment, the syntax is the left-hand side equals the right-hand side. In a non-blocking assignment, your syntax is left-hand side and you use this particular symbol, less than or equal to. Now, it turns out that this symbol right here is also used to represent less than or equal to. But the context in your Verilog program will indicate whether it is a less than or equal to operator or a non-blocking assignment. Incidentally, where this comes from is you may have seen this type of symbology used in some of your math courses. That's supposed to represent an arrow. So this is the Verilog way of doing this type of assignment. Now, as far as what these mean, blocking means the left-hand side is updated before the next statement executes. Non-blocking and this is kind of a new concept, which you probably have not encountered before. Non-blocking means the right-hand side is evaluated and recorded. Left-hand side updates at the end of your initial or always block. Now, just as a side comment here, we're going to visit blocking and non-blocking assignments multiple times in this course. And we're gonna find out whether you use blocking or non-blocking assignments has ramifications when it comes to students. So blocking, I'm going to update my left-hand side before I go on to the next statement. In non-blocking, I'm going to just record the right-hand sides. I'll evaluate it if it's an expression, but I'll just record them. And then when I get to the end of the initial or always block, all the left-hand sides immediately update. So let's look at a couple of examples. We're going to do two initial blocks here. The first one, I'm going to have some variables A and B, and they will get values of 3 and 2 respectively. And then in the second initial block, I'll have that. Now, we know that the initial blocks all begin executing at time t equals 0. So, and initial blocks only execute one time. So after both of those initial blocks have executed, what is the value of A and B? Three. Any other answers?
Is it undetermined?
Undetermined. Any other answers?
But sorry, are you asking after all of this executes?
I'm sorry?
Are you asking, sorry, all of this executes after all of this?
Yeah, well, both initial blocks begin executing at time t equals 0. After they've executed, what's the value of A and B?
A is 2, B is 3.
So I've had, they're equal to 3, undetermined, and you said A equals 2, B
Oh,
equals 3.
sorry.
The definition all had to say both equal to.
Are you claiming both of them are equal to 2?
Yeah.
When the first initial block finishes, incidentally, how long does it take to execute that first initial block? How much time?
She's done before the primary.
Remember I said, you need to get your mind right. How long does it take? Any pound sign delays in there? So how much time does it take?
Start.
0. Don't think about executing on a processor, you need to think, get your mind right on the way the Verilog program simulates. The initial block, the first one at the top, executes in 0 time. So you have A equals 3 and B equals 2. The second initial block also begins executing at time t equals 0, but you'll notice that the first assignment has a 10-time unit delay, after which A equals B. Now, the first initial block is already finished because it executed in 0 time. So I have A equals 3, B equals 2. So this statement right here is after 10 time units, A will equal 2, the value of B. The next statement then executes. You notice these are blocking assignments. B is equal to the current value of A, which is 2. So A equals B equals 2. Okay? Is that clear? All right. Second example. My first block is going to be the same. Here's my second block. Now the only differences have changed from blocking assignments to non-blocking assignments in the second initial block. When both of those initial blocks have finished executing, what is the value of A and B?
Do they swap?
This is going to wait 10 time units, and then it's going to record the right-hand side. What's the right-hand side? Well, B has a value of 2, and A has a value of 3. Those get recorded. When you hit the end statement, the left-hand sides immediately, simultaneously, concurrently update. So they swap.
So, how does it know what that command is versus the less than or equal to command, which looks similar, or is it the same command?
I'm not sure I understand the question. Say that again?
So, there's a less than or equal than command in the relational operator types.
Tell by syntax,
Oh,
or I should say context. The context here is I'm doing an assignment. If this was embedded in a if statement, then the context would say, do a comparison. Well, I don't have an if statement or anything similar to that. It's just standalone, so it's obviously an assignment. Does everybody see the difference between blocking and non-blocking assignments? They're not the same. And again, you need to get your mind right on the way these things simulate. Everything simulates in 0 time unless there are delay elements, or as we will see later in this lecture, events. Incidentally, the #10 is required. Otherwise, you run into race conditions. Consider these, the first two, and let's suppose I didn't have that in there. They're executing in 0 time. That would pose a real problem. The #10 says even though both of these blocks begin executing at time t equals 0, there is a ordering in there enforced by the #10. So this assignment will complete before you get to this assignment, even though the two blocks begin executing at time t equals 0. You just delay 10 time units and then do your assignment. Do you have a question?
Yes. Would it be fair to say that the pound sign 10 is almost a blocking statement?
No.
Because,
Don't think of it that way. Just think of it as, I'm waiting. Don't try and infer that this is blocking or non-blocking. Blocking or non-blocking is determined by which equation, equality operator you use, assignment operator. That's the only thing that determines blocking and non-blocking. The pound sign 10 just establishes an order between the two initial blocks. Now, a couple variations on this. You can put delays on separate lines if you wish. So I could do something like this. In this case, I'm just not gonna do anything for 10 time units. And then immediately in 0 time, I'll set A equal to B. Once that assignment's done, I'll go on and do B equals A. So you can put those on separate lines if you wish. And you can also use expressions. Here I've got a variable on delay, and maybe I've defined that with a parameter statement. And you'll notice that my delay, which is, since it's an expression, it's done inside parentheses. I'm saying whatever the value is of on delay, you divide that by 2. So you can have a mathematical expression for the delays if you wish. Now, just to reiterate a point, which will become intuitively obvious to the most casual of observer shortly in this lecture. Delays are not synthesizable, but they're useful in test benches. And as we've said a couple of times before in this class, when you synthesize, you synthesize designs. You don't synthesize test benches. So the fact that I've got them in test benches is not a problem, because test bench is only used for simulation purposes. So I want to look at an example here. I'm going to use a parameter statement to define on delay equals 3 off delay equals 5. So I've got two variables, on delay and off delay, with values of 3 and 5 respectively. So I'm going to define a reg variable A. And you remember that reg variables can only be assigned values where?
When they're declared an initial or always statements.
They have to be inside of an initial or an always statement. It's the only time you can assign a reg variable a value. So I'm going to have an initial statement where I give A a value of 0, and then I'm going to have an always statement now. You'll notice that I'm using blocking assignments. As a matter of fact, I'll put that in a comment just so that you are aware of that. Now, I'm interested in what kind of waveform that particular code will generate. So,
On for the first 3 seconds. It'd be on for 3.
A would look like this, and this is not to scale. But A initially has a value of 0. On delay, which has a value of 3, A goes to 1. And there's a delay now of 5 time units, and it goes back to 0. Right? But this is an always loop, so it's always executed. So go back and do that again. Delay 3 time units, go to a logic 1, wait 5 time units, go to a logic 0. Wait 3 time units, go to a logic 1, wait 5 time units, and go to logic 0, and so on. So that would be the waveform that I would generate. Those delays are relative. 3, and then 5 added to 3 gives me 8. 8 plus 3 is 11. 11 plus 16, 11 plus 5 is 16, and so on. These delays are relative to each other. That's an important concept. Okay. Now you can use something called a intra-assignment delay. Or a regular delay. are terms that your author uses, and I don't want you to get hung up on terms. This is the only time I'm going to, well, it may not be the only time. You're not gonna have a homework assignment or a test question on the difference between an intra-assignment and a regular assignment delays. I just want you to be aware of the two ways that you could specify delays. Now, technically, these are not the same. If you look at those, it appears like they would be the same. A equals, gonna wait 2 time units, now I'll tell you the value of B, do your update. And this one here, wait 10 time units, now make A equal to B. They seem to be accomplishing the same thing. Technically, they're not the same. So the question is, why not? And so I want you to consider the following. If I look at this intra-assignment delay, this is equivalent to the following. Begin, I'm gonna set hold equal to B, delay 2 time units, and then set A equal to hold. If you look at this, A equals, wait 2 time units, now I'll tell you the value. Store the current value, wait 2 time units, now update. So this is equivalent to that. Here's the problem though. Hold is going to have the current value of B. You're then going to wait 2 time units. During those 2 time units, B could change value. So when you do this update in this third statement, remember these are blocking assignments. So when you do this update, you may not have the most current value of B.
But could something else change hold? Or am I reading that
That's
wrong?
No. But during that 2 time unit delay, B could change to something else.
But it doesn't matter, right? Because you're assigning A equals hold, or?
My goal is to have A equal to B. It's not going to be if B
Oh.
changes during that time period.
Okay.
Now, if I look at the regular delay, it's equivalent to in this particular case, and this is equivalent to what I have in the previous page, A is going to get the current value of B. So the intra-delay assignment may not give you the most current value, the regular delay assignment will. So that's why I say technically they're not the same. Now, if it turns out B did not change during that 2-time delay, then A is gonna have the most current value of B. If B changes during this 2-time unit delay, doesn't matter because A is gonna be set equal to the most current value of B. So technically, they're not the same, even though just a cursory glance may suggest that they are. Okay, so to get a good handle on the difference between the regular delay and the intra-assignment delay, I want to diverge and talk a little bit more depth about test benches, and none of this stuff is in your text. So it turns out that the initial statement is useful for generating waveforms. So for example, let me do the following. Okay, now, again, these delays are relative to each other. So if I plotted reset, initially I have a value of 0, and again, this is not to scale. At 100 time units, reset would go to a logic 1. 80 time units later, so that would be at 180, it goes to a 0. And then you delay 30 time units to 210, and it goes to 1. And that's what you would get for the waveform based on that initial state. So let's try this. Left out the beginning and end. Okay. So what would that give me? Well, initially reset is equal to 0. Then reset is equal to, wait 100 time units, and then set it equal to a 1. Then reset is equal to, I'll wait 80 time units, set it equal to a 0. Then reset is gonna equal, I'll wait 30 time units, and then set it equal to a 1. Okay? So it looks like the regular assignment and the intra assignment gives me the same result. Now, what do you see that's different?
The numbers, you make them less relative,
The numbers wouldn't get updated until the start of the next cycle.
The numbers are not.
What's syntax? Syntactically, what's the difference?
These are non-blocking statements.
All right, I went to non-blocking assignment. Anything else?
The numbers have changed because they're no longer relative to each other.
Syntactically, not semantically. What's the difference between the two programs?
the numbers?
The numbers are different. Okay? Because here I had 100, 80, 30. Here I've got 100, 180, 210. Those are all relative delays. When you have non-blocking assignments and you're using the intra-assignment delay format, those delays become absolute. So this gives you the same waveform that you had before. It's just now I've told you precisely what time to make the change. Yes?
Just so I understand, if you change that, reset that, reset 180 0 to reset 80 0, basically what will happen is that would resend the reset signal to 0 at 80 seconds. Is that,
No, this does it at 180.
or, I'm sorry, if you had it at,
Correct. If I had put 80 in here, then at 80 it would have gone to 0. But because these are absolute delays. Now, before we go on, before I answer your question, let me point out one other thing. Since those are absolute delays, the order doesn't matter. This says, since this is the non-blocking assignment, record the right-hand sides. We'll update at the end. So this says, immediately, give me a value of 0. Wait 100 units, give me a 1. Wait 180 time units, give me a 0. Wait 210 units, give me a 1. Those are all recorded. When I hit the end statement, I get the update to the left-hand side. So I could swap the order of these and it wouldn't have any effect at all. That's the value of absolute delays. Obviously, order does matter if I'm using blocking assignments, because those are relative delays. But these are absolute, so order doesn't matter. Yes?
If we put a blocking delay in the middle of those,
Let me make this statement now. Okay? You never do that. But you pick one. Inside of a initial block or an always block, either they're all blocking assignments or they're all non-blocking assignments. You never mix and match. I'm just trying to figure out the semantics of that. Could be mind-boggling. Yes?
That was my question as well.
Is this
Oh, okay.
because we'll break this simulator, or because it's technically incorrect, or just because it's too difficult to understand?
You just don't. Okay?
should we compare that to like,
This is order doesn't matter. If you start putting blocking assignments in there, also there's a reason which I won't get into yet. In descriptions, which you do synthesize, if you mix always and, I'm sorry, if you mix blocking and non-blocking in the same always block, it creates havoc with the synthesis. Okay, so just don't do it. It's a hard and fast rule. To show you the advantage in writing your test benches using this absolute delay, and I'll do this as an example. The advantage would go to non-blocking assignments with inter-assignment delays if you have a complex waveform. Let's suppose I wanted the following clock signal. Nah, better not call it a clock. I'll call it C. And this is not to scale. Let's suppose those are the time units when you wanted the signal to change. You want to figure out what the relative delays would be for
Sounds
that?
fun.
Could be tedious to try and figure out what those are. But with the non-blocking assignments and the intra-assignment delay, it's trivial. That's where they occur. So if you've got a complex waveform, that's why I say the advantage goes to this non-blocking assignment with the intra-assignment delays. If you got a real straightforward waveform that's it's regular, it's periodic, etc., maybe not, but if you have a situation like that, there's definite advantage in using that particular technique. Okay, let's take a 10-minute break. Thank you. You know something? Yeah, you'd just be generating the same thing. So if it's in the always state, if you're gonna repeat the waveform, in fact, that's a good fun, I should bring it up. Right, if I wanted to do this and repeat it, so now I'm gonna wait 57 time units and then set this back to it again. 57 time units. Then do an normal log. Yeah, you probably want to use
Instead of using it,
the absolute is just generate the same thing. So you'd only get one waveform. So that's it. That's it. Yes.
To clarify, that was because the area for assignment is not walking around. If you append, say, a pound from the beginning of the statement, to the count 10, then the user thinks that it's like this line, once I this entire thing is one statement. This is the same statement. Okay, but if I have this execute what? Immediately, this will execute that time.
First of all, is non-blocking assignment. It's gonna go through the initial, they always block, and immediately record the current value of the right-hand side. And if you tried to simulate this, this would actually wait 5 minutes. These updates are all during the same time, separate So, in this particular case, time T was 5, that was, but the right-hand sides all get recorded in time T.
Okay, right, I see, right hand side, oh, so right hand.
They were doing the driver.
Also, they did that too.
You said I did it like,
No, it's at the end.
No, it's gonna come in this way as well. So you're gonna wait 5 time units before they get updated. But these will be updated with the values that you had at the T.
I see. When the values are captured, when the right hand side is captured and when the.
They're all captured in time T.
Yes.
Even if you had inter-assignment delays, it's still gonna capture the current value.
Yeah, they came by and had like.
And then use that value back.
And then subject to the delays, they'll dictate when the.
All right.
So you did not do
Yes,
good.
sir.
Yeah, so they were like.
So,
"What
yeah,
is
no,
it?"
but-
Yeah, I was like, you seem like you're because they were, for their drivers, they were running into a stream where they pass it back and forth. And their issue was they were doing scans, or they were doing a scan on, yeah.
Gate level?
And I think one of these scans was like, okay, we need to, they were taking this buffer, which was stacked. They were just passing it, scanning it, and then I could see their numbers, like they type in, 247 in here, and it would be 247, and then like a bunch of shit from the buffer. I was like, you need to set your buffer to null it out, because or else you're just gonna be passing in. Because then they were like calling Springland, and I was like, wait, when you call Springland, you don't know what the zero is. And then they weren't.
Probably we need to split these out. This is gonna assume, this is just a basic mortgage.
I used the string.
So I'm gonna have to have.
I was like, oh, we should send this.
Yeah, I should probably go like, another
Oh, you did? Why, what happened?
It's logical operating. This is the bitwise operating.
class I had. I did that too.
Oh, if this is logical.
What
Oh, they're asking for the logical operating.
Data sheet.
Yeah, that's what happened to me too. I had to ask about this.
It's a little bit problematic trying to do a
That chart is wrong.
It could be a negative number. So it's not because I think you said the way this thing works is this will have a value.
Yeah, that's what I started to do. I mean, there was he said don't do, and he was like, don't set the control light over everybody, just do it.
I started to when I was in
This is a golden expression, it doesn't necessarily.
yeah, and there's
That wasn't clear.
that's what these mean.
So what are you doing, eight other descriptions? Oh, yes, you don't have to stay in the same level. So I could have this here. And in addition to that, under nozzle I put up where I have data flow,
Oh, with full.
behavioral, and gate level, I said, when do these execute?
Or no, you are one.
Except for one project. So you can mix levels
No, that's
of
the first
abstraction.
project,
So
372.
if that's what you're
wait,
doing,
wait, plus timer,
I'm sure how you would do that.
But the plus is
Unless you tell me something
Yeah,
about.
it's at the very
It's like the very last thing.
Did you bring, sweets for everyone? Sadness. I shouldn't complain. I have chocolate cake in my car. I never forget.
That goes, I mean, it's good.
Yeah. I'm worried.
The video lectures, I just haven't gotten around. I just haven't watched the lectures on
They were fun, but I get it either way. But I mean, yeah, it's more like, you know, just saying that. If you have someone else watching, I get it.
It's like the data sheet, what it says to here, the data sheet doesn't actually work. There's like different data sheets for the same thing. One of them is
Is that possible? Can I do that? 'Cause I declared-
And you know how they show you an example of the initialization of the Python, you need to set
But you don't need all the logic line.
explain there. Like if you make your own list of the stuff that you need, like you say, you want first line, like what two lines. If you just get the price that you need to do, it doesn't work.
First number,
This is extra bit that like it doesn't say in the.
Yeah, so you have to decide, follow what they say, and then whatever extra stuff you wanna do, you can do that after. Just like doing all zero.
it's not zero. In this case, I would treat that as a logic zero.
This is the only time.
In this case, I would treat it as a logic one. Because it's on zero. So now I got just a zero or a one, stored with just a zero or a one. And the definition is, if it's non-zero, it's a logic one. That's the notation. So the answer to that one is actually kind of easy.
That inspired, there's a lot of.
All right, let's continue. Event-based control. Oh, I'm coming back to this. He brought up a good question. If I had, let me use one of my examples here. Go back and you look at this one. What would happen if instead of a conditional statement in there, I had an always statement?
Just try and do the same thing over and over.
You just do the same thing over and over and over. This would not generate a repeating waveform.
Because they're absolute values, right?
Because they're absolute values. If you look at the example I had at the beginning, there's your always statement. Those are blocking assignments with relative delays. That gives you your repeating waveform. Okay. But if you try and do that with the intra assignment and the non-blocking assignment, you're just repeating the same thing over and over again. They're absolute delays. You get once through and nothing else changes. Okay? All right. So now, event-based control. The @ symbol is used to indicate events. And so this is going to be very effective when we're trying to describe devices like flip-flops that respond to clock edges, or latches that respond to levels. Purpose of event-based control. is to synchronize activities in the module. Okay, it's just like a flip-flop, it only responds, Q output only changes, only can change when you get a clock edge. And it has to be the right clock edge, either the leading or the trailing clock edge. There are two types. Edge triggered and level triggered. And both types of event-based control will use this @ sign to indicate the event. So I want to start off with the edge triggered. Those are two Verilog keywords. What do you think they stand for?
The positive and the negative edges.
Positive and the negative edge. But we have to define what we mean by a positive edge and a negative edge. Because recall in Verilog, you have 4 possible values. Logic 0, logic 1, don't care, and high impedance. So if I look at a signal like this, that's the positive edge. And that's the negative edge. A positive edge is defined in Verilog as any transition from 0 to don't care, 0 to high impedance, 0 to a 1, don't care to a 1, high impedance to a 1. In short, you have a positive edge event if you change from 0 to something else, or anything that changes from something else to a 1.
And
The negative edge is 1 to a don't care, 1 to high impedance, 1 to a 0, don't care to a 0, high impedance to a 0. Any change from a 1 is a negative edge. Any change to a 0 is a negative edge. So, let's look at some examples. For that statement right there, the semantics are as follows. A is going to equal B. However, that assignment does not take place until that signal undergoes a positive edge transition. Then that assignment takes place. So you can see where we're getting synchronization here, because I'm waiting for an event to occur and then I do something. In this case, an assignment. Okay. Give you a couple others. I'm gonna wait until the signal D undergoes a negative edge transition, and then I'm gonna get, set Y equal to, a logical AND of C and B. What do you think that one does?
Any change?
Okay, this is an example, these are edge. And this is an example of a level. This says any change will cause the assignment to execute. Okay? So there are a number of examples. We'll take a look at a couple of those shortly. I want to make
Should those be in always or initial blocks? Or would they just be, they would be outside of that, right?
yeah, I'm gonna get to that. Now, you can put an event on a separate line to cause a wait. So I could do something like that. Or I'm just gonna wait here. As soon as I get a positive edge of the clock, then I'll go on. And I do this assignment. These are blocking assignments. So this has to elapse before you go on to that. And of course, I could, or events, for example, I could do something like this. This would say at positive edge of the clock or negative edge of reset, set Q equal to 0. When you have ORed events, you only have to satisfy one of them to satisfy the event. So at example 713, text shows a variety of these. positive edge of the clock, Q equals D. Q equals D is executed whenever the signal clock changes value. Because this is level-based control, I don't have pos edge or negative edge in there. Any change in clock, the assignment takes place. Here I'm specifically looking for the positive edge. If I get a negative edge, it's not gonna have any effect. It's gonna still wait. This would be for a negative edge. Ooh, look at this. I put my event on the right-hand side, not the left-hand side.
That's like doing delay on that side.
I want to make this a note. Those two are not the same. Why not?
Because you don't know what value of D necessarily, or?
No. In this one here, you're gonna sit there and wait until the clock changes, and then Q equals D. Here, I'm going to say Q is equal to, and I'm going to wait until I get a clock edge and then get the value of D. When this event is satisfied, this is immediate, it's the current value. Here, you're setting Q equal to something, but you're waiting till an event occurs and then getting the current value. Slightly different effect.
D could change while you wait for the clock to change, right?
What?
And the second statement, D could change in the meantime when you're waiting for
Oh,
the
sure.
clock. So it's just similarly to what we.
Yeah, this you're waiting for the event, and then Q, whatever the current value of D is. Here I'm saying Q is equal to, wait for it, and D could be changing 15 times before you get a clock edge. And then you get the value. So, these event triggers are like assignment of reg variables, are only done inside of a initial or an always block. And here's some examples from 715 where I have an always block, and I have multiple things that will satisfy the event. Any change on reset, any change on clock, any change on D, and I go into the always loop. Now you go all the way through, execute all the statements in the always loop, get to the end, and go back and the next event to occur. So if I don't have an event list, it just continually loops in an always loop. Keep going back to the statements over and over and over again. But if you've got an event list, and you've got to put this event list on the same line as the always statement. You execute the always statements only when the event is satisfied. Okay. Now, I want to look at example 717. So I have always at A or B or C or D or E or F or G or H or P or M. And then I have a couple of if then else statements. And if you look at the variables in the event list, they're all on the right-hand side of this expression, of these two expressions actually. So what that says is, if anything changes on the right-hand side, update out 1 and or out 2. Now, with this long of an event list, if I've got all these variables and if any of those variables change, I want to do an update. There's a possibility I might leave one of those variable names out of the event list. Let's say, for example, this is rather complex. Let's suppose I left H out of the event list. Device would not operate the way I expect. If you have a situation where any change to any variable on the right-hand side is to satisfy the event, there's a simpler syntax where the asterisk is a wildcard. And you can use either one of those versions. I prefer the version in parentheses because it keeps with the standard notation of at enclosed in parentheses, you have your events listed that you're looking for. So this code down here is the exact same thing, except you'll notice they have an asterisk instead of the enumerating each one of the variables. One other statement, I tend to call this the event list. Your author calls it a sensitivity list. Same thing. If statements, yes.
What's the difference between an always at wildcard compared to just an always statement?
Because you have to get a change in one of those signals to get an event.
But if none of them are changing, then
Then you just sit there and wait. Right?
I'm not seeing the difference between having an event to trigger something changing if something changes compared to just.
This
sitting
was
there.
not a particularly good example. The only thing they're trying to show in there is the fact that there is this wildcard operator so that you can control the length of your event list. You don't have to be constrained on a complex design to, let me figure out all of the variables to make sure I've got them all, because I only want to do the always statements if a variable change value. And if you're using event control, that is the only time you will execute all the statements. So now the question is, do I want to enumerate all of them, or do I want to just say, I'll use the wildcard because I've got too many to worry about? If then else. Now your author believes in taxonomies. So he's got a type 1 conditional statement, a type 2, and a type 3. I don't care if you memorize type 1 or type 2 or type 3 at all. I remember the types. Basic if, do that. The second type is if that's true, do that, else, do that. And the third type, if that's true, do that, else if, else if, else if, else if, as many as you want, terminated with a else. So I remember it that way. It's if true, do this. If, then else, if, then else, if, else, if, else, if, else, if. Now, one thing to be aware of is in some programming language, I think, if I remember correctly, MATLAB is this way, else if is one word. In Verilog, it's 2 words. 2 words. So here are some examples. This one says if lock is logic 0, or it's false, then not lock would be true. If that statement is true, buffer equals data. If enable, out equals in. Here's an example. If number queued is less than max queue depth, then you execute these statements. Else, you execute this one. This right here, $display, the syntax of that, that's a system task. The syntax of that is identical to printf in C. This displays something on standard app, your screen. And the syntax inside here is identical. You can use /t for tab, /n for new line. You can have variables in there. You can use the %D, %F to represent the format of the numbers that you're displaying. Just think $display is the same as printf in C. And then here is a type 3 statement. It's just an else if, else if, else if. And what they're doing here, what they're showing you is, let's suppose that you had an arithmetic logic unit. And this arithmetic logic unit is simple. It's only capable of doing 3 things. Adding 2 numbers, subtracting 2 numbers, or multiplying 2 numbers. If ALU control equals 0. Now notice, since you're doing a comparison and not assignment, you have to use the double equal sign, just like you do in C. If ALU control is equal to a 0, you perform the addition. Else if it's a 1, you perform the subtraction. Else if it's a 2, you perform the multiplication. Else display invalid ALU control signal. So that's how you can describe a ALU. So this is pretty straightforward. In C, we have something called switch statements, which you should be familiar with, right? Verilog, we have case statements. Not called switch, they're called case. And the syntax is nearly identical to what you have in C. Keyword case, keyword end case. You have some expression. Here are potential values of that expression. So these are individual values. There's your keyword, that's the catch-all default, just like in your switch statement. If none of these hold, then that's your default. Now this is statement 1, statement 2, statement 3. You could have multiple statements in there. If you do, you must have begin and end. Okay, but you could put, if expression is equal to alternative 2, you could have 58 things that you do, but you must have begin and end. So this again is example 718, and we saw how you could build up a simple ALU using if-then-else statements. Here's how you do it with a case statement. Case, ALU control. If it's equal to 2-bit 0, you do the addition. If it's a 2-bit binary string of 1, you do the subtraction. 2, you do the multiplication. Your default is display invalid control signal. Functionally, your case statement and an if-then-else statement are identical. So which you would probably want to know, why does Verilog provide both? If they both do the same thing, functional.
Which one is a lot easier to pick?
Well, it turns out, and we will get to this later in the course, in some circumstances, the synthesizer will recommend that you use a case statement, and in other situations, it will recommend that you use if-then-else statements. So the rationale of which you should use is a synthesis issue, not a Verilog description issue. Let's look at some examples. How about a case statement for our old friend, the 4x1 multiplex? So you recall, I have a single output, 4 inputs, 2 select lines. Depending on the value of the select line, determines which of the 4 inputs gets hooked up to the output. Module, end module. Give it a name, mux 4-to-1. There's all of my port signals. There's the declaration. Here's my always statement. You'll notice that what you're doing here is you're updating out, but you only update out when S1 or S0 or I0 or I1 or I2 or I3 changes, which makes sense. If one of my inputs changes, I'll want to do an update. If my select lines change, I'm choosing a different input to hook to the output, you want to do an update. Otherwise, there's no point doing the update. Hence, you've got event control. Now, I have highlighted something here in yellow. This is a common use for the concatenation operator. If you look here, the way you have declared the module, you declared S1 and S0 as separate signals. In the case statement, you're treating S1 and S0 as a 2-bit binary string. Well, it's decimal, but it's represented by 2 bits. So you have to take those 2 individual bits and form them into a 2-bit string. Notice how that was done with the concatenation operator. It takes 2 separate signals, forms them into a binary string, so you can now represent your case attribute by different values. Does everybody see how that's done? This is an important concept. This is done quite frequently. Okay? Now, in the examples that we've looked at so far, high impedance and don't care are treated literally. They have to match as well. Let me give you an example here. Let's suppose that A is a 2-bit binary string and has a value of 1, 1. When that executes, what's the value of B?
Zero.
Well, I heard 0.
Oh, no, it's 1.
Well, that's annoying.
If you use case statement, everything's gonna match. This is not equal in a case statement. May be true logically, but it's not true in the case statement. Two other operations that you have are case Z and case X. These are both keywords. If you use case Z, any Z bits are ignored. And if you use case X, all X and Z bits are ignored. And what I mean by ignored is they're not part of the comparison. So, let's suppose I had used case X instead of case. Same as before, except I've got case X in there. What's the value of B now? Why? Any bit that has a don't care or a high impedance is ignored. The only bit that has meaning is the least significant bit, and that matches. Because I have a don't care there. Okay. This is a rather complex example. First of all, this is a demultiplexer. Demultiplexer has one input and multiple outputs. The input is connected to one of the outputs based on the pattern that you put on the select lines, just the opposite of the multiplexer. So in this case, I have a single input. I have 4 outputs, out 0, out 1, out 2, out 3, and 2 select lines. So there's my port declaration. Notice that out 0, out 1, out 2 are declared as wire variables, and then redeclared as reg variables, which means I have to be in a always statement to assign the values. Not initial statements, always statements, because presumably I want to synthesize this, and initial statements are not synthesizable. Okay, so the first part of that is pretty straightforward. Always at, if your select lines change or your input changes, think about the way the demultiplexer works. You have a single input connected to one of 4 outputs. If you change the select lines, I'm hooking the input up to a different output. Obviously, I want to update everything. If I haven't changed the select lines, I still have the same output and input connected together. If the input changes, I wanna update the output. So in either one of those cases, I wanna update the output. So, I have an always statement, and there's my select lines or the input. You gotta think about the circuit and how you wanna describe it to figure out what needs to go into the event list. Also notice, for a demultiplexer, I'm not looking for edges. I'm looking for changes in logic state. So you don't see pause edge or negative edge in this event control. Any change on the input, any change on the select lines, update the outputs. Yes?
Could you do an always on a bus? So like if any bit in the bus changes?
Yes.
Okay.
Will this generate, how about the efficiency of the code that it generates? Will it use more LUTs?
I'm not gonna get into code efficiency, I'm trying to teach syntax here. Okay, so, you'll notice in the case statement, they're only worried about the select lines. So there's your concatenation operator, form those into a 2-bit binary string, and there are the 4 possible values. Actually, there's more than that, but we'll get to that shortly. 0, 0, 0, 1, 1, 0, 1, 1. Begin. And you'll notice that there is an output update, regardless of how the select lines change. If I have 0, 1, let's say, hooked up, then the input is hooked to out 1, and so you'll notice that out 1 is equal to in. The rest of them are put in the high impedance state. See how that works? So if I change it, if I don't change the select lines, I'm not changing what output is connected to the input. So, but I do have the input as part of the event list, so I'm gonna go through here again regardless. And you'll notice that if I haven't changed the select from 0 to 1, if in changes, it satisfies the event, I go through the always loop, and you'll notice that I will update out 1. That's why in is not part of the case expression, only the select lines. And the other inputs are high impedance. Now, they went through on this, and I'll give a comment on this shortly. They said, well, okay, that covers S1 and S0 being 0, 0, 0, 1, 1, 0, 1, 1. What if the select lines are, and notice how they have done this. You have 1, 2, 3, 4, 5, 6, 7 case attributes that all produce the same result. You could put those all on separate lines. But if you have multiple attributes that all have the same effect, you can put it on one line separated by commas. This is the same thing you do in switch statements. So, you'll notice that if the S1 is a don't care, or S0 is a don't care, I make the outputs all don't care. If S1 is a high impedance or S0 is a high impedance, I make the outputs all high impedance. Otherwise, I default unspecified control signals. Now, this is not synthesizable for one reason. These system tasks are not synthesizable. So you'd never have a $ display in a module you intend to synthesize. That said, as far as an editorial comment on here, This was done for completeness, but you would never specify this in an actual design.